Okay, I'm going to re-record, redo a video that I've already done, and the video and the sound were not so great. So I want to redo this video because I think it's kind of important. Alright, so I'm going to talk about geometric series and why I think that 0.9 repeating equals 1, which you either learned in school to be true, or maybe that sounds completely crazy, or maybe you learned that it wasn't true in school, but I'm going to claim that, that it is true, and I hope to prove that in this video. Okay, so a quick overview. First, I need to describe some other series that are not, well, I need to talk about some equations first, and then first I need to talk about these particular series. Then I'm going to talk about why 0.9 repeating, in my opinion, has to equal 1, and then the third thing I'm going to talk about is Zeno's paradox, which is often talked about in calculus classes. Okay, so first I want to talk about this series. So this is really r to the 0th, anything to the 0th is 1 plus r squared plus r cubed plus r to the 4th, all the way to r to the n. Now, I'm going to set this as infinity, and n is actually going to go to infinity. So this is a little bit sloppy how I have it here, but hopefully you'll go along with me for a second. So let's look at this series. So I claim that this is true. In fact, you can just ignore this part, but I claim that this is true, that if you keep adding it over and over and over again, all of the powers, that you can actually just have this simple result here, that 1 minus r to the n plus 1 over 1 minus r. That is true, and this would be true for all n that's inside the natural numbers. Okay, so I have to talk about this before I talk about geometric series. So let's get into proving this. Alright, so I'm going to use mathematical induction. Maybe you already know about this, maybe you don't. It's a super common way of proving things in math. It's essentially any class that you take on proofs, you're going to need mathematical induction. So the first thing to do is to show that the number 1 will work. Alright, so I'm going to show that number 1 works. So instead of infinity, I'm just going to make it 1. So n's going to start at 0, and it's going to go all the way to the number 1. Well, that's just going to be r to the 0th plus r to the 1st. Okay, well, anything to the 0th is just 1. And let's see if that works. So that would be 1 minus r squared over 1 minus r, if we plug that in. Alright, well here, hopefully you've seen this before in algebra class. This is the difference of squares. 1 is a square, 1 times 1 is 1, and r squared is a square, obviously it has 2 there. So this is the difference of squares. We can factor that as 1 minus r, 1 plus r, or the cross terms we can see are going to cross out. You're going to have negative r plus positive r. Those will cancel out. And what happens is you have 1 minus r over 1 minus r, and this part reduces to 1, and so all of this just goes to 1 plus r. Okay, so I just put a little check mark there, and it says that yes, if n equals 1, this is true. That seems totally irrelevant, but if you do mathematical induction, the first thing you have to show is that what is it when n equals 1 case. Alright, moving on. Now I have to show the k plus 1 case. Okay, so for k is some number in the natural numbers. If p of k is true, then pk plus 1 is true. That's the claim. Let's see. So we're going to go all the way to the n, and then we're going to go to the n plus 1 case. So we're going to go one more. So if I do this in the formula, what's going to happen is I just put the n plus 1 here, but then I also have to add the r to the n plus 1 factor here. Okay, well, through some algebra, it's somewhat tedious. It would be about 1 or 2 slides of just algebra, but you can show that this is true. That just adding these two you can get here, that you can go from here to here. Well, that actually is all I need to do. I just need to show that the n plus 1 case is just going to be this is going to take it to the n plus 2. And that's all I really need to do. So thus, the p of k plus 1 is true when p of k is true. Then by principle mathematical induction, p of n is true for all n in the natural numbers. And then this little square just says QED. That was that which was supposed to be shown. Okay. So that's all you do with mathematical induction. And really all I'm doing is I'm showing that this is true. I need to show that this is true for this series. Okay, moving on. Now, Bernoulli's equality. This probably seems totally unrelated. Prove that the absolute value of x less than 1. If the absolute value of x is less than 1, then the limit as n approaches infinity of x to the n goes to 0. Alright, that sounds really complicated. It's not at all. It's saying that if x was a number between 0 and 1, so like you could think of a decimal, you could think of a fraction, like a half, a fourth, a third, maybe x was a third, and then as this approaches infinity, it's going to get smaller and smaller and smaller, and it's actually going to go to 0. Remember, we're doing limits here. I just want to remind you that we're going to do limits here. We're not doing sums, so I wouldn't add those up because obviously the sum wouldn't equal 0. It's the limit. It's going to approach 0 as n goes to infinity. Okay, suppose first that x does not equal 0. Okay, well, in my example, I was already not doing that, but just to show you, since the absolute value of x is less than 1, the absolute value of x equals 1 plus 1 over y for some y greater than 0. Alright, so I will use that if 1 plus x is greater than 0, then 1 plus x to the n is greater than or equal to 1 plus nx for all n inside the natural numbers. Alright, mathematical induction again. Got to show that the first one's true. So I plug in 1 for that. So you get a 1 here, you get a 1 here. And all I showed that 1 plus x is greater than or equal to 1 plus x. And of course that's true because 1 plus x is equal to 1 plus x for every number ever. Okay, x could be any number. It doesn't have to be a natural number for this to be true, but we're just claiming that it is. Alright, now I have to show the k plus 1 proof. Okay, well this is a little bit more algebra, so I plug in k plus 1. I goofed up on the parentheses here, so I apologize about that. This should be lifted up in the exponent. I should have corrected that. Anyway, so you do some algebra, and lo and behold, all you really discover is that 1 minus 1 is greater than or equal to 0, which we know is true because 0 is equal to 0. Okay, so what did I really show? All I really showed was that this statement is true. That if x is less than or equal, or no, just less than 1, it can't be equal to 1, that wouldn't work. If x is less than 1, or in between 0 and 1, then the limit of x to the n as n goes to infinity is 0. That's all I really need, but I threw in the proof here. And specifically I want to talk about the 0 case. Alright, so with those two facts, the limit as n goes to infinity of r to the n plus 1 goes to infinity, or goes to 0, excuse me, when r is less than 1. Here I'm turning r into, our x is less than, or our x is now an r. Okay, now if you plug in the 0, then you have 1 minus 0, 1 minus r, so you get 1 over 1 minus r. This is what we need. This is your geometric series. This is everyone's geometric series. This is what we require. Now, that seems confusing that I would need all of that just to show that 0.9 repeating is equal to 1. There's other ways of showing this, but geometric series, I think, is a fantastic way of doing it. Okay. So let's get into it. This is why I think that 0.9 repeating equals to 1. Alright, so first let's go line for line. 0.9 repeating, I claim, is the same thing as the sum of n going to 1 or n starting at 1 and going all the way to infinity, of 9 divided by 10 to the nth. This is commonly shown. They probably showed it to you one time in grade school or grammar school, and then you never saw it again unless you took college math. But you can represent decimals as 10 to the nth, as n is getting, or 1 over 10 to the nth. Okay, so this is getting smaller and smaller. All this is that these two things are the same thing. All right. Now, I can do this. I'm not gonna prove this. This is such a trivial thing, but you can multiply this, that this would be the same thing. The 9 is not changing with the sums. The only thing that's changing is this n, and then it's adding up. So I can pull out that 9. That's a very trivial proof. I'm not going to show it here. Anyway, so I pulled out the 9, but I kind of need the 0. I need this 0 here for it to be the geometric series. If you remember, I have to start at 0. So I have to kind of manipulate this, and I have to take the 1 case out. For these two things to be true, I'm going to have to subtract 9. I have to subtract, or you can think of, if this was still like this, it would be minus 1. Okay. So this is our geometric series. This sum right here is our geometric series right there. Or that is a geometric series. So from here to here, the 9s stay the same, but this is my geometric series. I have 1 over 1 minus 1/10. I still have the 9 because I need it for this, and I have this minus 9 because I need to take it away because I went from 1 to 0. So I have to subtract that off for it to be the same thing. Now comes just simple arithmetic. Anything 1, so this is 10 over 10 minus 1, so 10 minus 1 is 9. Alright, so now I have 1 over 9/10. That's just the reciprocal of 9/10, so you get 10/9. You multiply these, that goes to 1, so you have 10 minus 9 equals 1. Okay? That seems kind of crazy, but it is absolutely true. And you can use geometric series, as I've shown here, to show that that's true. So I hope that somewhat helps, or that makes any sense, but I think this is a really neat result. Okay, so Zeno was part of, or he was Greek. He's part of the Greeks, and there's a thing called Zeno's paradox, and Zeno was thinking about this idea of, he was thinking about, what if you walked halfway somewhere? So let's say you're going to cross the street, and to cross the street, you would have to eventually make it halfway across the street. And then after that, you'd have to be halfway in between your current position and the end of the street, right? And then you'd have to go halfway again, and halfway again, and halfway again. So you keep dividing in half, but he didn't understand how you would ever actually make it to the other side. It doesn't seem like it would be an infinite process. You would never actually be done. So how could you ever get there? He knew he could cross the street. I mean, he wasn't like a total crazy person. But the idea is that he didn't mathematically understand how you could represent the idea that you eventually do get across. Okay. So what does that have to do with anything? Well, here is the Zeno's paradox. This is the thing that he couldn't quite figure out. So if you walk halfway, then you'd walk a fourth more of the way, you'd walk an eighth more of the way, a 16th more of the way, and so on, and so on, and so on. But what does this sum equal? Does it equal infinity? Because you're adding positive numbers infinitely. So diverge only means, is this going to go to infinity? It might go to infinity kind of slowly, because these keep getting smaller. Or does it converge, which means that it would just equal a number. It would just go towards a number. I'm going to show you that it actually does go towards a number. But it was puzzling of why it doesn't just go to infinity. Now, it wouldn't go to infinity super fast, but why doesn't it go to infinity? Well, we can use our geometric series that we've developed to find that out. Okay, so once again, I claim that we can do this. We can go 1/2 to the n and just over and over and over again. But for this, to use my geometric series, I have to do it to the 0. And I really want to start at 1 because I want to start halfway. I want to go half and then fourth. But just because of the way the math's set up, I have to start at 0. So I have this extra 1 here. Well, I'm going to take that extra 1 away because I don't want it. Not for what I'm showing. So here you can see that I need to subtract that first one there. So -1. Okay, so it's 1/2, and you're just going to keep going. So this will be 1/2, and then 1/4, and then 8, 16, 32, so on, so on, so on, so on, so on. Okay, now, going from here to here, there's no real change, but this is a geometric series. This right here is a geometric series, and I already showed the result that that's 1 over 1 minus that ratio, that r. And then here we can just use just basic arithmetic, which would be 2 over 2 minus 1/2. Well, that's just half itself. Or you can think 1 minus 1/2 is 1/2. This is just the reciprocal of 1/2, which is just 2. So you have 2 minus 1 is 1. Okay, so now we have what Zeno couldn't quite figure out. Now you have it. In 2019, solved. It was solved analytically. I think I'm trying to think, when was it analytically solved? I shouldn't have gone on this tangent. I think certainly Riemann and Cantor put the absolute nail in the coffin of that this is officially a dead question. But I'm sure there's someone else that found this result. I'm not sure if Isaac Newton. I don't even really know if he did much series or not. I don't know. He did a lot of limits, but I'm not sure about his series. But certainly, late 19th century mathematicians. They were the ones that really developed this series. The way we used our notation now. So they would be the ones that totally killed the question. Okay, so that is the end. That's all I really wanted to talk about. A few things that were going on in my head when I was talking about this. I don't want to show you that not everything's going to equal 1, right? I'm just showing 2 fun examples I'm thinking of that happen to equal 1. These are the most interesting to me, and they just happen to equal 1. But you can imagine now you have this technique. You could really do any problem you want. If you believe me that you can use this formula, basically it just boils down to a formula that if you can think of a ratio between 0 and 1, and you can represent it this way, then you already have the answer. You have 1 over 1 minus the ratio, and you already have the answer if it goes to infinity. So it's super helpful, and it's usually gone over in your first year calculus class. You'll usually go over that, but I promise that it's more interesting than your first year calculus class may show you. Okay, so my motivation for this is not actually even academic. It's just for fun. I'm almost done with this book, Everything and More. It's actually pretty short. As you can see, it's only about 300 pages. And it's written by David Foster Wallace, who is not a mathematician, but he took a lot of math classes in college, and I think he almost majored in math/philosophy a couple of times in his academic career. He's actually famous for another infinity book called Infinite Jest, which is just a novel, or not just a novel, but it's a novel. It has little to do with math, and it's fiction. But this is an excellent book. It actually explains the history of how they were thinking about infinity, which may sound boring to you, but I promise is actually interesting. And it's this book is more interesting than any calculus class I ever took. or any analysis book. I don't know if you've ever taken analysis, but analysis is basically proof-based calculus class, which is very rigorous, but it's not very interesting. This is about the people that developed it, and moreover, how they were thinking about it and how they came across it. But so I highly suggest this book, and he does go over these two results, and much more. I may do even more videos that come out of this book because I really enjoyed it. Okay, so again, I'm just redoing this video because the last time I did it, I had both video and audio problems. I'm hoping I don't today. And I hope that you somewhat enjoyed this video, and if there's anything I left out or could have went on a bit more, please post in the comments. But until next time, thanks for listening.